So one of the questions that was asked by one of our students over email was, how does imbalanced data impact logistic regression? And he asked us if we could explain it geometrically. So let me try to construct an example for you so that you understand it better. Imagine if I have a bunch of positive points. Let's assume all these are my positive points. I'll try to create a simpler example so that you understand it better. And let's assume I have 20 positive points. Let's assume I have 20 positive points. And let's assume I have 3 negative points here. Right? Let's assume I have 3 negative points. Obviously, this data is highly imbalanced because you have lots of positive points and fewer negative points. Now, what is a hyperplane that we expect logistic regression to return in a case like this? We would want our logistic regression to return a hyperplane somewhat like this. Okay, so let's call this plane pi1, and let's assume my w1 is in this direction. So all positive points are in the direction of w1, all negative points are in the opposite direction to the normal, right? Which means both positive points and negative points are correctly classified, right? That's an important part here. Number one. Number two, let's look at our optimization problem that we solve as part of logistic regression. We try to find a W that maximizes sum of sigmoid of or logistic function of, right, yi w transpose xi, right? Look at this. This is your signed distance. On the signed distance, I'm applying a squashing function like the sigmoid, right? And I want this to be maximized. I want my W that maximizes this, right? That's the whole goal that I'm trying to achieve. So given this data set with 20 positive points and 3 negative points, let us understand which hyperplane maximizes, because I'm trying to find a W, right, which maximizes this, isn't it? So let's see which hyperplane would the logistic regression return. So let's take two options. First option is this yellow line. Let's assume the second option is a blue line somewhere very, very far away. Let's say some blue line here, very, very far away, right? So let's call this plane pi2 and let's call this direction w2, right? Simple. Now let's look at this. When I take pi1, right? All these points are at some distance. All these points are correctly classified. All these points are also correctly classified because these are on one side. These are on the positive side of my plane and these are on the negative side of my plane, to put it simply. Now let's assume the sigmoid of the distance, right? Remember, this distance is non-zero, right? And how does the sigmoid function itself look like? The sigmoid function looks like this, right? The sigmoid function looks like this. So if you have yi w transpose xi on the x-axis, right? If you have the sign distance on the x-axis, if the sign distance is 0, the sigmoid function has a value of 0.5. If the sign distance is infinity, it has a value of 1. If the sign distance has a value of minus infinity, it has a value of 0, right? So if the distance is not 0, but a small value like this distance, this is not 0, right? The sigmoid of the sign distance, let's assume here, is a value of 0.8. Similarly, let's assume the sigmoid of the sign distance for these 3 points is also 0.8. So what happens to this formula here, which I'm trying to maximize, right? I have 20 points, which are at a distance of 0.8 here. This distance is basically, what I mean by distance here is sigmoid of the sign distance. I have 20 points whose sigmoid of the sign distance, these 20 points here, is 20 into 0.8, because I have the summation here, right? I need to summate all of these 0.8s and all of these 0.8s plus 3 into 0.8. This 3 into 0.8 corresponds to these 3 negative points. This 20 into 0.8 corresponds to this orange points. So this total value, 20 into 0.8 is 16. 16 plus 2.4 is 18.4, right? Now let's look at pi2, okay? In the case of pi2, what happens? If my logistic regression returned, or if it created this W2 as the answer and not W1, right? If it returned, because at the end of the day, what is the logistic regression trying to solve? It's trying to solve this optimization problem internally, right? Now let's look at this. Let's look at each of these distances, right? These distances are very, very large, right? Because these points are very far away. Let's assume this hyperplane pi2 is very, very far away. then what happens? These distances are very large. And when distances are very large, which means your yi w transpose xi is very large. And for these points, it's positive. For these positive points, it's positive because your w2 is pointing in the same direction. So this direction is the positive direction for your pi 2. This is your negative direction. There are no points in the negative direction. Both your positive points and negative points are in the positive direction, right? So what happens to yi w transpose xi? It will be positive large number here for these 20 points. Okay, your for these 20 points. Okay, let me find a place to write it on this page. Okay, so let me write it here. Okay, I'll just erase this and write it here. So if you take pi 2 for these 20 points, I have 20 multiplied by sigmoid of a large value. Sigmoid of a large value is close to 1 because sigmoid function flattens at 1. It plateaus at 1. It doesn't go beyond 1. So it's 20 into 1 because these distances are large. So these distances are large, right? Now what about these points? Now what about these points? These distances are also large. Of course, they're slightly smaller than these green distances to positive points, but still this is large. But your yi, now what happens is your yi w transpose xi for negative points will be negative because all these points are actually negative points, which means your yi is -1, but w transpose xi is going to be positive. So your yi w transpose xi is going to be negative large values, which means what happens to sigmoid of negative large values? They become 0. So 3 into 0. So what do I get here for pi 2? 20. At the end of the day, I'm recapping this. At the end of the day, your logistic regression is trying to solve this optimization problem. Whichever w maximizes this sum is the one that logistic regression will return. So if logistic regression has to choose between pi 1 and pi 2, it will choose pi 2 because the sigmoid of the sign distances, when I sum them up, pi 2 gives me a larger value than pi 1. So when you have an imbalanced data like this, right, because there are many positive points here, what happens is your hyperplane will move as far away as possible from these positive planes so as to correctly classify them while incorrectly classifying all of your negative points, right? So in this case, what's happening? Whenever you give any new query point, your model will say positive class, positive class, positive class. But even though because I have fewer negative points, that's why this whole thing has happened. Imagine a world where I have, let's say, 20 positive points. Let's say you might have 20 positive points and I have, let's say, 20 negative points. Same number. Okay. I'll show you that this problem cannot occur when you have 20 positive points and 20 negative points. When you have this, let's take our pi 1 first, right? Our pi 1 will be here. Let's assume our pi 1 is here. Okay. Our pi 2, let's assume, is here. Now what happens from the perspective of pi 1? All these distances are 0.8. The sigmoid of the sign distances are 0.8. So you get 20 into 0.8 plus 20 into 0.8 because you have 20 positive points and 20 negative points, and they're correctly classified because your W1 is in this direction and all these points are correctly classified. All these points are also correctly classified, right? So what do you get here? You get 32 because 20 into 0.8 is 16. 16 plus 16 is 32. Now what happens from the perspective of pi 2? From the perspective of pi 2, right? All these distances are large. All these distances are large, right? And sigmoid of a large number is going to be 1. So I will get 20 into 0.1, sorry, 20 into 1. I'm sorry, you'll get 20 into 1 plus all these points. Now look at this. All these points are correctly classified and hence you have a positive value here. All these points on the other hand are misclassified, right? Because these points should be on the other side of the plane, right? If I use this as a hyperplane and say all these are positive points and all these are negative points, of course all my blue points are misclassified, obviously, right? Because they are misclassified, they have large negative distances. So your yi w transpose xi is going to be a large negative value for each of these blue points, right? If you have large negative value, the sigmoid of large negative values is going to be equal to 0 plus 20 into 0. This total value is 20. Now look at it. What is logistic regression trying to achieve? It's trying to maximize the sum. It's simply trying to maximize the sum. Now, if it has to choose between pi 1 and pi 2, pi 1 resulted in a sum of 32, pi 2 resulted in a sum of 20. So it will obviously choose pi 1 and not pi 2, unlike the previous case. In the previous case, it chose pi 2. And this is happening because I have fewer points of the negative class, and I'm okay if I make a mistake in that, right? But in this case, if I make a mistake on my negative points, because the number of negative points is the same or very similar in number to the number of positive points, right? It will not allow us to accept a hyperplane like this, which only classifies one class correctly and misclassifies everything. I hope this example helped you understand how imbalanced data impacts logistic regression from a geometric standpoint. And I strongly recommend you to think about it from these examples. We have seen similar examples even in the video content. So constructing these examples and trying to dissect what's happening will give you far more clarity on what's happening. I strongly recommend you try out things like this to understand what's happening internally, especially from a geometric standpoint.